Okay, we have now described the basic physics behind the induction motor, the torque production in a very popular manner. Let's now make a few big jumps into the details of the machine and modeling of the machine. Of course, if you want to do this more in detail, you have to go to courses on electrical machines and drives, but hopefully I will be able to give you a quick and brief introduction to the operation of the motor, also by doing some simple calculations. This shows a single-phase equivalent circuit in steady state for an induction motor, a three-phase induction motor. So this is a single-phase model, so all quantities are single-phase quantities. And it's also a stator-based one, which means that we have recalculated all the parameters so that we have a stator equivalent model for it. This is of course for steady state and not for dynamic calculations, but it gives us a good idea of the basic operation of the induction motor, as I will show you now. So what are these different resistances and reactances? Well, let's start with a simple one, stator resistance. This, of course, corresponds to the resistance of the stator winding. That is the copper winding in the stator. So it's a pretty obvious part of the model. The second part is R2 prim, which is the rotor resistance in stator reference frame. That is, we have taken the rotor value and calculated to a stator reference frame, or to a stator model, which makes it possible to introduce it in this kind of simple steady state model. Anyway, that is the rotor resistance corresponding to the resistance of the rotor winding, or the cage winding in the rotor. The magnetizing reactance is a measure of, or it's the reactance or the inductance between the magnetic flux, air gap flux, and the corresponding magnetizing current. This is typically, well, it's a relation between flux linkage and current. That is the definition of inductance. And this is of the magnetizing inductance. And multiplied by omega, that is the magnetizing reactance. This magnetizing reactance, it's of course different for different kind of motors, different kind of pole pair numbers, and of course it's determined by the shape, the design of the magnetic circuit of the motor. Typically, the magnetizing reactance will decrease by increasing pole numbers, since we then have to magnetize more air gaps, as I will show you later in the picture. Compare with, for instance, a transformer, which has no air gap, or basically no air gap at least. The value of the magnetizing reactance for traction motors or induction motors are lower. That is, we have a higher magnetizing current, IM, than for transformers, for instance. The next part is this resistance, 1 minus S divided by S times R2 prim. That is the mechanical output power of the machine in steady state. That is, this resistance is equivalent to, if you calculate the power delivered in that resistance, that will be the same as the mechanical output power of the motor. This is an electric model of the mechanical output power. And the last part here is XK. So what is XK? Well, XK is leakage reactance due to the leakage inductances. And leakage inductances, they are due to the fact that not all flux is linking both the rotor and the stator. So that is, leakage fluxes are fluxes that do not link stator and rotor. This is an example where it only links the stator winding here. That is, it doesn't cross the air gap, goes into the rotor and back to the stator. These are typically called leakage fluxes. I have a better picture perhaps here showing the leakage fluxes of the stator winding here. That is, these leakage fluxes can be modeled as this leakage reactance. And this leakage reactance is really important for the total operation of the machine, because it determines a few of the important parameters of the machine. Well, you try to minimize it, but still it's very important to have. So this circuit now is of course possible to use for calculation of the steady state performance of the motor. But we'll make a few more simplifications also from this picture. I will take away or remove or neglect the stator resistance. It has influence, especially when it comes to control of induction motors. It's really important, but for us in this case, we try to find more of a qualitative description of the machine itself. It doesn't really have to be part of the simplified equations. The second part is the magnetized reactance. Of course, it's important and it contributes to the current of the machine, to the stator current, but also in this case we simplified it by avoiding this parallel connection in the single phase equivalent circuit. That helps us in putting up the equations for the output power and torque produced in this resistance here. So the simplified model is as shown below, with only the leakage reactance, the rotor resistance, and the resistance that, so to say, where the power is produced. Assume now that we apply a voltage, stator voltage, three-phase voltage, and in this case, of course, calculate as a single-phase voltage, on this machine. Calculate the power and divide by omega to obtain the torque. That is, the torque is the mechanical power divided by the angular speed of the rotor. And this is of course then given by 1 minus the slip times P12, where P12 is called the air gap power. That is the power that goes from the stator into the rotor of the machine. Then we have the mechanical speed, which is lower than the synchronous speed, 1 minus S, the synchronous speed. And if we put up P12, it's 3 times the resistance where the power is in the rotor, and times square of the current. And if you do this calculation a little bit, well, continue to calculate it, you get this expression. We can see that the torque of the motor is determined by the resistance of this rotor circuit, applied voltages, and of course the leakage reactance and slip, where the mechanical speed is 1 minus S times the synchronous speed, and the mechanical power is 1 minus S times the air gap power. S times the air gap power, that is S times P12, that corresponds to the losses you have in the rotor circuit. So if you have, let's say, 5% of slip, it means that 5% of the power transferred into the rotor will be losses in the rotor circuit. And that is, of course, a reason behind the quite significant losses you have in the rotor of an induction motor, which is demanding for the drive and for the design of the drive. So if you plot now this equation, you get these torque characteristics for the induction motor. This is a very well-known curve that describes the torque as a function of the speed of the machine, or as a function of the slip down here. And as we discussed before, or the torque at zero, or at rated speed, at the synchronous speed, or that is slip equal to 0, that is 0. So there is no torque produced at synchronous speed. If the rotor is lagging, that is, the rotor is rotating at a lower speed than the synchronous speed, the torque will start to increase, like this. And without any kind of leakage reactance, the torque would just increase by increasing the slip of the machine. But of course, we don't have that kind of, any kind of drive has a leakage reactance. So there will be a limitation in torque, and that peak value is called breakdown torque. Breakdown torque is the peak torque you can produce from an induction motor. Sometimes also called pull-out torque, but breakdown torque I think is more common. So you can see that we have rated torque here is where you normally design, is the torque you normally design the motor for. That is, at rated torque, you you have the thermal limitations, so to say. That is, at great torque you can produce this torque. You can produce this torque continuously for a long time without overheating the machine. But if you want, you can overload the machine by increasing the torque further up to something normally referred as maximum torque. So you have rated torque, you have, sorry I lost that here, rated torque, you have maximum torque, and you have breakdown torque. You have 3 different torques. And the train drive itself, or the traction drive, normally utilize up to maximum torque. You don't want to go to breakdown torque, of course, then you stop the machine. But maximum torque and rated torque are the 2 important design parameters you have in the drive. On the other opposite, if you have a drive where the rotor rotates at a speed higher than the synchronous speed, then the motor starts to operate as a generator. That is, the machine goes from motoring to generator operation and starts, for instance, if you have a traction drive, a propulsion system with induction motors, when the train starts to brake and regenerate power from the train to the power supply, it means that the machines start to generate this way, that the rotors are rotating with a higher speed than the synchronous speed. And this curve for generator operation is a mirror of the one for motor operation. That is, this is the same kind of curve as that one. If you would have added the stator resistance, it wouldn't have been perfectly symmetrical. That's why that's why we sometimes take away the stator resistance when we try to describe the background to these equations. Just a little bit, some comments about this picture here and the design of the machine. As I mentioned before, pole pairs are important, or pole numbers are important. And 2 poles, that is 1 pole pair, 4 poles, that is 2 pole pairs, that are different designs of different machines. And as you can see from this picture, what happens when you increase the number of poles is that the magnetizing inductance, if I go back to that one, this magnetizing inductance will be smaller and smaller, and the magnetizing current will increase. And this magnetizing current it's phase shifted 90 degrees from the active current, so to say. It's a purely inductive current. So what will happen is that we get a higher inductive current by reducing the number of poles. That is, machine will get a poorer and poorer cosinus phi. The power factor will be reduced, and for a drive, you will use, for a certain given output power, active output power, you have to consume a lot of reactive power, making the rated or the apparent power bigger, and you have to design converters or inverters feeding the machines, the motors, for higher power. So from that point of view, you normally want to have a rather limited or reasonable number of poles. Traction motors are typically designed for 2, 4, 6, that kind of number. I would say 4 or 6 poles are pretty common. What happens with 2 poles is that the end windings become too long, that you lose a lot of the active volume in the machine. So 2 poles is not as attractive as traction motor. So normally go for 4 poles and perhaps 6 poles. Hardly higher numbers than 6 poles. Because if you go to 8 poles, you will have a cosinus phi down to perhaps 0.6, 0.65, forcing us to have a pretty much bigger 3-phase inverter feeding the motor. Let's have a look finally at speed control of induction motors. We'll come back to that in the next lecture, but this is an introduction to different measures to control the speed of the induction motor. What we can do is, of course, to change the slip, because we learned that the slip determines the speed of the rotor. If the slip is larger, we'll get a lower speed of the machine. So, and we can do that, for instance, by changing the voltage. If we change the voltage, this breakdown torque will go down. So let's say if you lower the voltage, the breakdown torque will go down. And that will generate a slope of this curve that is less steep. That is, for a given torque, load torque, we will get a different operating point, that is a different slip and a different speed. So this is one way of controlling the speed of the motor, by controlling the voltage and in that way controlling the slip. You can also, if you want, change the rotor resistance. That would be to move this point. The breakdown torque occurs at a specific slip down here. If you increase the resistance, you will move this breakdown torque peak to the left. That is, it will occur for another speed. That is, for another slip. So both of these methods, voltage or rotor voltage change or rotor resistance change, will change the shape of the torque speed characteristics of the induction motor, and thus it will change the speed for a given load torque. But what are the drawbacks of this? Well, if you change the slip, it will change the rotor losses. Especially if you would like to lower the speed, it will increase the slip and you will increase losses in the rotor. So this is not a lossless control of the induction motor. It generates even higher losses than it does in normal operation. So this is really something you can do only in specific cases. And it's not a useful way of controlling the speed in a traction vehicle, in a train or in a car, whatever it can be. So in this case, we can use it in some cases, but not for trains. So the second option would be to change the synchronous speed of the train, of the motor. That is to change either the pole pairs of the machine. So that is, you go from 2 poles to 4 poles and so on. You can do that. It exists old-fashioned methods to change the pole numbers in operation by changing the connections of the machine, but that's not at all either a possible way to do in trains. That's a little bit of a historical aspect only. So the other option you have would be to change the frequency of the applied voltage. So the stator voltage frequency is changes the synchronous speed of the motor, and thus it can be controlled. It can be used to control the speed of the rotor as well. So, summarize the speed control. There are a few different methods you can use, but in principle only one that is practically possible to use, and that is changing the frequency and the voltage of the applied voltage in order to change the rotating or the synchronous speed of the motor, and thus be able to control the rotor speed as well.